Hi students, in this session we will talk about the estimation of population variance using the sample data. So we are often interested in determining what is the behavior of any variable in the entire population in two ways, that is what is the mean value and what is the variability related to that variable. We talk about income, we are also interested in the fact that what is the mean income of the people who are living in this city, as well as what is the average variation that we can call income disparity as well as a measure of income disparity. What is the average variation with respect to the mean value in the entire population, and that is represented with the help of standard deviation of the population. So to estimate the population variance, we need to first consider a distribution that may give us a connection between the corresponding sample statistic and the population parameter that we are interested in. And over here, we are interested in determining the relationship between the sample variance and the population variance, or the sample standard deviation and the population standard. And the distribution that we use for this purpose has the name chi square distribution. Chi is again an alphabet borrowed from Greek list of alphabets. That is chi we indicate in this way and we raise it to square. This is how we write it down. Chi square gives us a connection between a sample statistic S square and a corresponding population parameter sigma square using this structure. Over here you can take notice of one thing, that chi-square can never have negative values. Why? Because if we focus on variability or we talk about variability, we should have at least two observations with us, because on the basis of that two observations based data, we first determine mean value and then in the next step we can determine variance or standard deviation. But in case of one observation, we can't talk about mean and we can't talk about standard deviation or variability. So we should have at least two observations. So n has the least value of 2. So n minus 1 factor consequently cannot give us a negative answer. Variances can never be negative, whether it is a sample variance or a population variance. So in this formula, this is S square and sigma square that are representing sample variance and population variance respectively cannot give us a negative answer. Therefore, chi-square distribution does not exist with negative values, or it does not exist in the second quadrant, we can say, where we observe negative values for a variable we are considering. So it starts from 0, and this is the shape of chi-square distribution. It is a positively skewed distribution. And the norm that we follow, let's consider this borderline and this borderline. These two borderlines may be representing, let's suppose, 90% area under the curve. If you would like to indicate the areas above, so the area above this borderline, which is B, we divide remaining part as 0.05 here and 0.05 here, because we have considered central 90% area under the curve. Now this curve is not symmetric in a way, as we referred both t tables and z distributions earlier. What we did over there, we determine the lower bound with negative value and we indicate the upper bound with the same positive value. So this is not the case over here. This value of that is representing a would be a lower value of chi-square because it is closer to 0 relatively, and b, since it is far away from 0 value, it would have larger value of chi-square. So there are two values of chi-square that we are interested in. One is lower value of chi-square closer to 0. Another is larger value of chi-square that is away from 0. Now the norm to indicate the lower and upper bounds in terms of chi-square probabilities is chi-square. How much is the area above this borderline? It is 0.05. And if we consider this, then how much is the area above? We can determine it as how much is the area below, which is 0.05, and take away this 0.05 from 1. If we consider if the area below this borderline is 0.05, then area above this borderline should be 0.95. Okay, it can be alternatively stated as 1 minus 0.05 gives us the same answer. 1 take away the area below this borderline. Now I'm going to maintain a list that gives us for a specific percentage of CI. Again, we go for 5 specific percentages of CIs, starting with 80%. So if we consider 80% central area, for 80% central area, we get 0.10 here and 0.10 here. And these two bounds we can indicate as the lower bound must be chi-square 0.90 and chi-square 0.10. If you go for 90%, as I have shown over here, the lower bound will indicate chi-square with 0.95 and the upper bound will contain the area above this borderline as 0.05. So should be stated or mentioned as chi-square 0.05. Similarly, if we go for 95%, so this should be indicated as 0.05 because both the tail contains 0.025 areas above the borderline and below the borderline respectively. So this we can state as 1 minus 0.025, that will be giving you 0.975. That's easier to deal with or determining. Then 98% CI, for 98% CI, we know that in both the tail and areas, two tail end areas, we have to indicate 0.01 probability. So 0.01 over here and 1 minus 0.01 would give us 0.99. Similarly, for 99%, we know that remaining 1% should be allocated or assigned to both the tail and zones as 0.05 each, 0.005 each. So over here, we indicate the subscript of 0.005 and 1 minus 0.005 would give us 0.995. So this is how we can determine the values. And now we can go and see the chi-square table. How does it structure? Now see, this is page 1 of chi-square table. So you can see the subscript of 0.995. That is the lower bound for 99%. Then this is chi square 0.99, that is indicating the lower bound for 98%. Then chi square 0.975, that is indicating the lower bound for 95% CI. This column is indicating the lower bound for 90%, and this is indicating the lower bound for 80%. Now go to the next page because it has two pages, same as Z table. The second page contains the upper bound or right tail critical values. So see, this has a subscript 0.10. So when do we assign or allocate 0.10 probability of the right tail? When we are looking for 80% CI. So this is the upper bound for 80% CI. This is the upper bound for 90%. This is the upper bound for 95%. This is the upper bound for 98%, and this is the upper bound for 99%. And CMST table, you can notice one thing, that the first column is for the degrees of freedom. So again, we have to apply first the degrees of freedom to select a specific row from chi-square table to select an appropriate value of chi-square. And remember one thing, that you should be getting for any given percentage of CI two bounds or two different values of chi-square. You cannot indicate, as you have indicated in Z and T, the lower bound as negative value. There is no scope for negative using negative value for chi-square. Okay. Now I'm going to derive the formula for 1 minus alpha percent Ci in the same way as we did earlier. So I'm opening up a new page, and then I'm going to start. Again, I'm going to write down the formula for chi-square as n minus 1 times s square divided by sigma square. Then what we do, I'm going to draw the curve and would indicate 1 minus alpha percent Ci limits under this positively skewed curve. So if we take 1 minus alpha percent central part, then this should have the probability alpha by 2 and alpha by 2, and we have discussed already that the norm to indicate two bounds of chi-square under the chi-square distribution is chi-square alpha by 2 for this one, and chi-square 1 minus alpha by 2 for the lower bound, because this is how we have determined in all 5 cases the subscript of chi-square lower bounds already. Now we can state this as a application of probability that we are interested in determining chi-square value under the curve that has a lower bound 1 minus alpha by 2 and has an upper bound alpha by 2, and the total coverage within these two borderline is 1 minus alpha. So starting from chi-square 1 minus alpha by 2 borderline and ending at chi-square alpha by 2 borderline, we can see that the probability or coverage is 1 minus alpha. Now what we do, same as before, we only take this part and we will substitute chi-square value in the center. Now if we notice that currently sigma square, which is the population variance, is in the denominator, and we need to move it to the numerator. So what we do, we'll take a reciprocal throughout this inequality so that chi sigma square, which is the uh, population variance, should be moved to the numerator. So sigma square divided by n minus 1 times s square, this will also be moved to the denominator, and this will also be moved to the denominator. So we have made adjustment in every part of the inequality. But what about inequality sign? So to deal with inequality sign, or to understand the change, we need to consider this. 3 is a value greater than 2. Now if we take reciprocal on both the sides, then this inequality will be inverted accordingly. So this was the lower bound previously. If we take reciprocal, this would become upper bound. This was the upper bound earlier on. If we take reciprocal, this would become the lower bound. So this is how inequalities will be inverted whenever we take reciprocal of inequality. Now we need to get this denominator factor, the divisor part, removed from the center, because we need this sigma square alone to be there in the center. So for this, we multiply this inequality by the factor n minus 1 times s square. And we get this answer. Now, inequality is written in this way right now. Upper bound first, then the lower bound. And if you would like to change it to write it down in appropriate way, that is the lower bound first and then the upper bound. So this factor should be written down first, and immediately inequality signs will be inverted again. And now you can take notice of one thing, that chi square alpha by 2 is the upper bound. That means the higher value of chi square it possesses or indicates. Here, chi square 1 minus alpha by 2 is located closer to the 0 value, therefore it should have a lower value, and the numerators of both the inequality sides are same, constant. So what makes the difference in the answer? The divisor part or the denominator part. So chi square alpha by 2 value being larger or greater relatively, and this value, since it is located under the curve closer to 0, so this will be a smaller value relatively. So the basic rule of mathematics tell us, when we divide any number by a larger value, we get a smaller answer overall, and when we divide the same value by a smaller value, smaller answer, or smaller value, we get a greater value or greater answer in the end. So this is how we can come up with 1 minus alpha percent Ci for sigma square. That is the population variance. If we want to redefine it for standard deviation, so we need to mention it inside the square root sign. That's it. So this is s square and divided by chi square alpha by 2 sigma, and again square root on the right part as well. So this is how we derive the formula for 1 minus alpha percent Ci for population standard deviation. Now, same as usual, what I'm doing, I'm taking an example to apply this formula. I'm going to write down the formula again uh, here. It's n minus 1 times s square divided by chi square alpha by 2 inside the square root sign for the standard deviation, and right hand side is n minus 1 times s square divided by chi square 1 minus alpha by 2. Now example is of a soft drink dispensing machine. Let's suppose a soft drink dispensing machine is adjusted in a way that it should be pouring in the quantity of 150 ml in a cup or in a glass. Okay, so the quantity expected is 150 ml. Since variation is everywhere, so even though we have tried our best that exactly 150 ml should be poured in by the machine in each cup, but this is practically not possible. Some cups may contain greater quantities and some cups may contain quantities below or less than 150 ml, and that we can check with the help of standard deviation, which is the measure of variability. So now let's take that we have selected a sample size of 15 cups. We have filled 15 cups from that machine, and we did notice that the mean quantity, let's suppose, is equal to 149.2 ml. That is representing some sort of a deficiency as compared to the 150 ml yardstick. But we are not interested in the mean value right now. We are more interested in standard deviation. Let's suppose standard deviation, when we have computed, is of 7.2 ml. So if 7.2 ml is the standard deviation and we are asked to construct 95% CI for standard deviation of all the cups or all the glasses being filled by that machine. So this is how we use the formula in the same way. Over there, first of all, we need to determine df on the basis of the formula n minus 1. So 15 are the number of glasses that we have filled. Minus 1 gives us 14. And now we need to determine two values of chi-square from chi-square table. I'm going to write down first the subscript of those two chi-square values that we need to have. Since we are interested in 95% CI, so one value of chi-square should be 0.025 because equal probability of 0.025 we assign to both the tail ends. So one value should be 0.025 with 14 degrees of freedom. Another value of chi-square should be 1 minus 0.025, that is 0.97514. How did we determine this? 1 minus 0.025. Now we go to the table, go to the 14th row of chi-square table, and we will one by one uh, locate these two values from chi-square table. Now you see on the first page we get the lower bound, and lower bound is this one, upper bound is this one. So lower bound value is has a subscript 0.975. We go to the chi-square table and we did then note down the value. So this is page number 1. 0.975 column is the middlemost column in this table. We go to the 14 degrees of freedom and go to this 0.975 value. So the chi-square value is 5.629. We note it down. 5.269. 269 or 629. 629, that is. 5.629 is the chi-square value. 4.975 probability, or corresponding to 0.975 probability. And now we can check across 0.025 probability the value across 14 degrees of freedom. So 14th row again, and middlemost column is indicating 0.025 probability. So 26.119 is the value. 26.119 is the value. Now what we do is just a matter of substitution values in the formula. That's n minus 1 means 14 minus 1, sorry, 15 minus 1, s square. Over here we are given standard deviation, so we need to raise this to square. 7.2 square divided by, then we need to take chi square alpha by 2 value first, that is 26.119, so that we must be getting lower bound. Now it's up to you whether you work out variance first and then in the end finally you can determine standard deviation or transform it to standard deviation after taking square root. Now we are going to compute the values. You can also try on your part. Sometimes I forgot to keep my calculator with me, so I am using cell phone right now. So 14 times 7.2 squared and divide by 26.119 gives us the answer as 27.7, and that's for the variance. 78 it is giving us 786, so 79 we can round it off to. Similarly, 14 times 7.2 squared and then divide this by 5.629, and this is giving us 128.93. Now we take square root on both the sides. The square root of 27.79 is 5.27, and the square root of 128.93 is 11.353. This is how we get our answer for the population standard deviation. And we can interpret now this answer as, we can be 95% confident that the standard deviation of the amounts being dispensed by this machine lies between, or it is exceeding 5.27 ml and less than 11.35 ml. Now, what if the manufacturer or the supplier has set some standard that standard deviation should not be exceeding 5 ml because it would affect the customer's trust or consumer's trust on the supplier? If it is giving you the quantities with deficiencies, so today's world is a world of competition and someone may go for an alternative brand. So to cover that risk, manufacturers or suppliers always claim some value regarding standard deviation and they manage to control it. Otherwise, machine needs a repair if this is giving us standard deviation value much higher than the or exceeding the standard limit. So let's suppose we are taking that manufacturer has set the standard of 5 ml, that it should not be exceeding 5 ml. Sample has indicated already that it is exceeding 5 ml, but we cannot generalize the sample findings for the entire population. So for that reason, we have determined the population standard deviation using 95% CI with 95% probability. So over here, we have to look at the lower bound. Is lower bound is a value that is exceeding 5 ml standard for the standard deviation, a 5 ml value for the standard deviation that they have set as a standard. So this is the case. It is exceeding and it is alarming. So supplier or manufacturer has to do something to make correction in the machine. Machine needs a repair because it is exceeding the standard value set for the standard deviation to be less than 5 ml. So this is how we can make a comment and we can apply the concept or the principles of standard deviation in real life situations. So every brand makes sure that standard deviation should not be crossing the limits that they have mentioned on their packaging. In on a lot of commodities, on the wrappers of a lot of commodities, on the bottles of soft drink, we did take a notice of that established brands do mention the limit within which they vary the quantity or the quantity may vary. Not they vary the quantity, but the quantity may vary. So let's suppose a soap bar of 125 grams may the manufacturer may have mentioned on the wrapper that plus minus 5 gram difference you can have. So we can apply the same rule over there. We can collect the samples from the population. Let's suppose 20 or 10 or 15. The greater the sample, the greater the reliability of your findings. And then you can determine in the same way, construct 95% CI and do check whether the lower bound is exceeding or not that 5 gram mark. If it is exceeding, it does mean that we are being sold the less quantities, deficient quantities, and not otherwise, vice versa. Okay, so that's all for this session. Bye.